Thank you, Johannes, for the introduction. You stole my icebreaker questions, but that's okay. Uh, thank you guys all so much for attending the Effect Meetup here in San Francisco. I think this is the second annual meetup, I guess. But we're so excited to see so many faces in the audience that are excited to learn about Effect. The title of my talk is The Rise of Autonomous Software, Building Agentic Workflows with Effect. But what do I really mean by agentic workflows or agentic systems? Um, we're becoming increasingly surrounded by systems that operate autonomously, systems that can make decisions, dynamically adapt to their environment without really any human intervention. Think about like all the self-driving cars we see here in San Francisco. We definitely don't have those in New Jersey yet, but maybe soon, who knows? But these systems can process and analyze inputs, adapt and perform actions on their own. And that's really what I mean by agentic systems. These systems have agency themselves to take action. But as developers who are tasked with designing and building these systems, we are faced with an enormous amount of complexity. We have to make these systems fault tolerant. We have to make these systems scalable. We have to make them observable. And the list just keeps going on. And while these systems are not necessarily unique to agentic systems, when we throw AI into the mix, we sort of like exponentially compound the complexity that we're faced with. But so how do we like deal with all of this complexity? Well, I think one of the ways we can deal with it is by leaning into our tooling. We need tools that are expressive enough to model all of this complex behavior and interactions, while also maintaining the reliability, the scalability, observability that we need when we're building these systems. And I think this is really where Effect shines. So just a quick level set. In this talk, we're going to spend a tiny bit of time talking about agents, kind of giving a little bit of a definition of what they are, some common design patterns that are in use, and then some of the challenges. And we'll try to go a little bit quicker through this part of the talk so that we can arrive at the part that everybody's probably more interested in, which is the role of Effect and like actually looking at some code. A little bit about me. I think Johannes already gave a great introduction, but I'm based in New Jersey. I was originally a pharmacist in a previous life. I'm a huge Effect enthusiast. I've been part of the community for the better part of 6 years. I'm also a DevOps and infrastructure nerd. That's kind of how I got my start in the tech world. So if any of these topics are of interest to you, please get in touch. I'd love to chat. Maybe we can chat this evening. So let's talk a little bit about what is an agent. How many folks in the audience have like a working definition of what an AI agent actually is? All right, that's pretty good. Well, large language models have definitely changed the way that we interact with software. Historically, and I use the word historically extremely loosely because I think I'm referring to like 2 years ago, but in the AI world, I guess that's like an eternity. Historically, interactions with models were primarily and basically only in a request response format, right? You prompt a model and you immediately get the output of that model token by token returned to you. There was no opportunity for the model to improve its output. There was no opportunity for any refinement. And so you basically got what you got. But over time, we started to figure out ways that we could enhance the output of our LLMs, right? We figured out we could give these models the ability to reflect on their output before they actually returned it to us. So kind of giving it a feedback loop. We connected them with external tools. And by doing this, we were sort of already building up towards what we sort of define today as like an AI agent. And like, while there's really not like a universally agreed upon definition of an agent, there is one particular, I guess, set of characteristics that's the most cited. And this comes from Lillian Wang, who's the current head of safety systems at OpenAI and is a former head of applied AI research there. She maintains a fantastic blog. So if you guys don't know about it, go check it out. It's really cool. Where she provides overviews on various AI topics. And she really does a great job of distilling these down into more easily digestible kind of formats. And in her definition of an agent, she basically says that they have 3 components. The first is planning, the second is memory, and the third is the ability to use tools. For planning, agents should have the ability to decompose tasks into smaller subunits. Basically, take a complex problem, break it into smaller problems that are more easy to solve. And then similarly, as part of planning, the agent should be able to reflect on its output so that it can improve upon its mistakes. And if you think about it, this isn't really all that different from how we as humans approach solving a complex problem, right? We sort of do the same thing. We also, as humans, have memory, both short and long term, just like agents. For agents, though, their short-term memory is really in the form of what we can fit into a prompt. So everything about the prompt is kind of like the short-term memory of an agent. Whereas the long-term memory of an agent is more associated with things that the agent might fetch as part of a request, right? I think probably one of the most popular examples of this is retrieval augmented generation, where you might have a vector database that has some embeddings on a particular topic, and that agent can go and get that information to enhance the output it's generating for you. And then the third component here is the ability to use tools. So, for example, giving the agent the ability to search the web or run code in an interpreter. And I want to talk a little bit now about, now that we kind of have a working definition of what an agent actually is, I want to talk a little bit about agentic design patterns, like the ways that we actually build these systems. But it's kind of difficult to talk about this because, number one, the tooling in the literature surrounding basically all of AI is moving at a breakneck speed. So it's really hard for us to sort of keep up with what's going on a daily basis. And also, everyone's sort of taking a little bit of a different approach to building these systems. So classifying them becomes more difficult. But earlier this year in March, Andrew Ng, the founder of Deep Learning AI and a bunch of other things, presented at the Sequoia Capital's AI Ascent on what he thought was sort of next for agentic systems. And he classified the design patterns that he thought were going to become popular into 4 major categories. So we'll go through these one by one quickly. The first design pattern he thought would become popular over this year was reflection. So again, giving the agent the ability to learn from its past mistakes, right? Giving it a feedback loop. So an example here is having maybe 2 agents work together to write a piece of code, right? You give the agent a task to write code to solve a problem, and that agent can iteratively improve the output of that code. And then here in this example, we have 2 agents interacting together, but I want to point out you could also get reflection just with a single LLM self-critiquing its own work. The second design pattern he thought would become popular was connecting LLMs to external tools. So you sort of start to see the similarities between how Lillian and Wang define an agent and the design patterns Andrew Ng thought would become popular. And again, this is just giving the agent the ability to use something that's not part of its API, call out to a particular tool to perform some action. On the left, or I guess, yeah, the left here, we have a prompt where we want to know what the best coffee is based on reviews. So we give the agent the ability to search the web for reviews, right? And on the right, we have a separate example where we give the agent a word problem where it has to perform some mathematical calculation. And that agent can now generate some code and run it in a code interpreter we give it access to. So again, giving agents the ability to use tools can significantly enhance the output depending on the problem we're trying to solve. The third pattern is planning, which again, you can remember from Lillian Wang's definition of an agent. And the example I want to point out here is we're going to take a particular complicated task, break it down into more digestible problems that the agent can solve. And for each of those subtasks, the agent can use different tools to sort of solve the problem. So here in this example, we're prompting the agent to generate a picture of a girl reading in the same pose as the boy on the scooter, right? So the first thing the agent might do is generate a task to do a pose determination, followed by generating an image from that pose. And again, we can use different tools to solve these different tasks. And the fourth design pattern that he thought would become popular is multi-agent collaboration. And I think this is probably the most interesting one, where we use multiple agents working together to try to solve a problem. And I think a more frequently cited example of this is the chat dev architecture. So the paper that kind of explained this architecture goes through, a mock chat-powered software development framework where every agent has a particular role as if they were in like a software development company. And when you feed a problem into the beginning of the chain, it sort of goes through like the planning phase with the C-suite and then through the coding phase with the engineers, et cetera, et cetera. And on the other end, you hopefully get a comprehensive solution to the problem. But the idea here is, again, you have multiple agents that are working together to solve the problem. And I think if we think about the AI systems that are around today, Andrew was pretty spot on with his predictions, but I think what's becoming even more common is combining all of these tools into even more interesting design patterns. I think a popular one today that basically combines all of these pieces is the mixture of agents model, where you feed a prompt into the system, and you have multiple agents that are all evaluating that same prompt and generating output. And then you have an aggregator agent that is basically trying to pick out what the best version of the output is. And what's really cool about this is every single one of those agents in the framework has tools, the ability to plan, the ability to reach out to different sources of memory. So you can really get some high quality output with a relatively simple design, simple in quotes, because obviously the implementation is much more complicated than this picture. And we can add additional layers into this model, which is pretty cool because just by adding additional layers, you can continually improve the output that you're getting. But one thing we really haven't mentioned at all when talking about these design patterns are the challenges that we face when we actually try to implement these things, right? More agents, more problems, right? So whenever we're building these systems, we have to deal with a lot of different challenges. For example, error handling. We need these systems to be fault tolerant, right? We need to figure out what to do in different error states. We also, in the situation where we have multiple agents communicating together, this may be happening concurrently, and we need to have a principled approach to how we actually manage that concurrency. Also, if we have many different concurrent requests out there to agents to generate output, if one of those agents encounters an error, we probably want to interrupt what's going on with the other agents so we don't waste bandwidth, right? And observability is always something that we should be keeping in mind, but often ends up being an afterthought. In these systems, it's even more important to kind of try to make observability a first-class citizen. And the list goes on of challenges that we face when we're building these systems. Other types of complexity also exist that maybe are slightly more specific to agentic systems where we have really long-running processes. So you can think towards like your autonomous agents where the processes might last forever. Interactions with multiple models means you have to handle all of these problems across every model you're interacting with. And then streaming, right? Everything becomes more complicated when you start incorporating streaming and doing all of these things, but in a streaming context. But again, all of these problems are not necessarily unique to agentic systems. They're sort of things that we deal with every day when we're developing normal software. And so for those familiar with Effect, you know that these are problems that are pretty much addressed by the library already. We do a great job of handling all of these things. So why do I keep saying that when we're building agentic systems, we sort of compound the complexity? Well, the reason is that agentic systems are inherently non-deterministic, meaning for the same inputs, you don't always get the same outputs, right? You might call an agentic system with 3 different times, and for each one of those times, that agent may decide to call different tools or reach out to different sources of memory, and you may end up getting totally different output from those individual prompts. And so how do we deal with these non-deterministic pieces of software, these non-deterministic systems that are very hard to predict? Well, in an environment where non-determinism is the default, we believe that effect is the antidote, so to speak. Observability and monitoring should be things that are critical from day one when building these systems. Effect does a great job with handling those things. And don't just take our word for it. There are already plenty of folks building these systems with Effect and seeing great results because Effect really makes sure that these are things that you consider up front. Companies like Mark Prompt, you guys are here doing a great job with Effect. Expand AI is another wonderful company. There's so many more that are using Effect to handle these agentic systems. And the list goes on, and I could keep talking about the problems that we're trying to solve. But I do want to dive into some code. But before I do, I have a little bit of an announcement to make. Drum roll. So today I'm really excited to be announcing the alpha release of a set of Effect native AI integration packages designed to make integrating with AI foundation models kind of like a breeze, right? Things that it's just like writing normal Effect programs. Our goal is to help developers who want to build AI-powered software applications sleep better at night, just like we're helping, the developers who write non-AI-powered applications sleep better at night. Huge shout out to Tim Smart, who couldn't be here today, but did an enormous amount of work on these libraries and came up with a pretty spectacular API. But yeah, so I'm really excited. You guys should all go out and try it and let us know what you think. We're super interested to hear your feedback. So let's dive into some code. So we're going to build up a small example here of just a simple prompt that we're going to feed into a model to rewrite some code with Effect, right? Effect's AI integrations are designed to be completely provider agnostic. So you can write code once and plug in the provider later. So in this example, you can see we're importing the completions service from Effect AI, and we're calling it in our program. Interacting with the API of providers is also designed to be agnostic of the provider. We're trying to help unify the API so you folks don't have to worry about, am I calling this model and I have to tweak this particular configuration value or whatever. We want a unified API for calling your models. You can see here we're calling the create method on the completions API with our prompt. So let's start to think about some of the possible failure scenarios that we might need to deal with. One particular failure scenario I can think of right off the bat is if a particular call to a provider takes way too long, we want to time out that request, right? It's as easy as an effect.timeout here with whatever you want as your timeout duration. But we also probably want to have a retry policy where when we call models, maybe we want to have that request be retried in a principled way. So here in this example, we're going to retry our call to this particular model with a policy of only making that retry call every 500 milliseconds, no more than every 500 milliseconds, and only 2 times. But another situation that you can think of when you're doing this is if the timeout situation happens, we probably don't want to retry. We've already been interacting with that model for 5 seconds and we're waiting for a response. If we're timing out, we probably don't want to end up retrying that particular API call. So again, it's as simple as adding, excuse me, a while parameter to our retry and just filtering out for the timeout exception. So now we're only handling errors that actually occur as a result of our interaction with our model. And then I mentioned before that we want observability with default, by default. Again, simple as a with span on whatever effect program you're running. And we'll see an example later of this, but within all of our AI integration packages, you get automatic tracing throughout the lifespan of that request generated for you as part of trace. So if you plug in your trace exporter, you'll see the trace going through the actual integration with whatever provider package you're using. So we'll see an example of that, but a little bit later. So this is great, and it's cool and whatever, and we're doing things in a provider agnostic way, which is cool. But model responses can be really long. And oftentimes, we don't want to wait for the whole thing to come back before we do something with it, right? So what about streaming? How do we actually do this? Well, this is the program we had before, and this is the same program with streaming. So for the most part, you change out create for stream and effect for stream. And now you have a fully streaming version of this program. Same number of lines of code, and it becomes really easy if requirements change in your company to swap out the behavior of the program without having to sort of rethink the entire API design that you were coming up with. And I just want to point out, I don't know if this is going to work on my version of the screen. Let's see. So I don't know if you folks can see it up there, but in the environment of the effect, you'll see that the completion service that we're using to interact with the model is now a requirement of the program. So at some point when we're done, we need to actually plug in the model we're going to call. So let's see a little bit of an example of that. So at the moment, we only have an OpenAI integration package, but we're already working on integrations for a number of other providers. And our goal is to have most of the foundation models covered for you guys by default. But here we're creating a client to OpenAI. You can see it's pretty simple. All you really need to bring along is your API key. And what's cool about this is, we'll see this a little bit later, anything redacted throughout your program automatically gets redacted in your traces. So if somehow some sensitive value ends up in a trace or a log somewhere, it'll automatically be redacted for you. And then once we have our client built up, we can actually build an interface to the completion service that we want to interact with. So in this case, we're building a completion service that's going to interact with the GPT-4o model. But you could imagine that if you have many different models that you want to interact with, all you have to do is just create layers for the different models that you want to work with. And again, the client is pluggable in this scenario as well. So I just wanted to show a quick example of how we actually plug in the client. So this is the same code that we wrote before, but just sort of like pared down. We're still operating on the provider with our agnostic API. But you can see now we're actually plugging in our GPT-4o completions that we created in the step before. And another thing I wanted to point out, we were a little bit thoughtful about the cases where you folks might want to provide provider-specific configuration per provider configuration, however you want to say that, too many provides, so that if you are using a particular provider in your program, those configuration values would be applied. Otherwise, they won't be, right? So you can imagine if you want to have a piece of code, again, that's totally agnostic, you can just keep providing configs, and when that provider's in use, those configs would be applied. So I don't know how to do this in a way that's ergonomic, but a quick demo. Okay. This is a slightly expanded example of what we went through before, but essentially, I'm just prompting the model to rewrite this piece of code with effect. I will say in my tests, our model must have been trained on a very old version of effect, but we can still see what happens. And this is the streaming version, by the way. So you can see we wrote a completely provider agnostic program. We plugged in the provider at the end, fully streaming, no problems, all effect native. And then I think that I'm not necessarily the best hype man, so thank you, Johannes. And then I also wanted to give a quick showcase on the observability piece, because again, I think that the way we combat non-determinism in these systems is by making observability a first-class citizen, because the only way that you can actually handle non-determinism is with observability. So, whoa, where did my mouse go? Okay. This is interesting. Okay. Well, okay. I also wanted to give a little bit of an example of observability and how we handle that. So the AI integration packages, we're already dog fooding them in production. I don't know how many of you folks are a member of our Discord. Okay, whoever's not should join. It's a great community. But uh, we wanted to keep Discord relatively clean. We get a lot of questions, and we wanted to keep our channels from growing too exponentially when a questions answer ran, 60, 70, 80, 100 responses long. So we decided to implement a bot that would do auto-threading for us. But we also wanted to have a descriptive title for those threads so that we could track like the threads that we were a part of and make sure that like we're trying to respond as quickly as we can and track which threads we're a part of, what we were doing in that thread, etc. So we decided to connect our Discord bot with an LLM to help generate an appropriate title based on the message. There's a couple of other AI features in the bot, like generating issues for us based on the summary of the thread, etc. But what I want to show off today is how we use our Discord bot to generate titles for these threads and how we can observe that by wiring that up to a tracing exporter. So hang on, bear with me. Okay. So here is the code. Yeah, there we go. This is the method that we have in our like AI utils service in the Discord bot, which is used to actually generate a title for these threads. You can see, again, this is basically the same code that we were using before. And it's not too complex, pretty easy to reason about. And as you can see, we're using OpenAI. And then the usage, okay. The actual usage here, you can see we're logging errors when we need to. We have a retry policy enabled. We only have specific scenarios where we actually want to retry these interactions. But I want to draw your attention to this right here, this width span right here, and also the one that we were looking at before. So we trace everything that happens in our Discord bot. And because we do this, because we just provide those width spans, we get, hold please, traces generated for us we use Honeycomb for tracing, but the point being here is that up until this point, the AI generate title span, we were annotating those traces. Everything else that happens here was generated for us automatically. So these two spans were automatically added by our tracing, our AI client integration, and we have a whole bunch of information about what actually went on during that request. All the request headers, all the response headers, attributes that we pass in, and this is all done automatically for you if you're using the client integration, the provider integrations. So yeah, not to quote Tim Smart, but you get all of this for free. Okay, we're arriving at the end. So where do we actually go from here? Yes, we, the Effect team, are going to continue to do our best to add additional APIs to the AI packages. We want to integrate with more providers. We want to give you the ability to do things like interact with OpenAI's new real-time API. We want to provide all of those things through our AI integrations. So we're working really hard on that. But where's the future really taking us here? Hopefully, I've convinced you all by this point that Effect is the perfect fit for developing agentic systems. But how are we actually going to deploy and run these agents? These are, especially in the world of autonomous systems, where I think that that's where we're going. These autonomous agents may be long-running processes that might live forever. So how are we actually going to run these systems? Well, I'm really excited about what we're working on. Unfortunately, there's not enough time for me today to talk to you all about it. But stay tuned. we're working very hard in this direction, and I hope that the next time I talk to you all, I'll be able to share a lot more. So thank you all for your attention. I really appreciate it.